Hey everyone! Welcome to our hands-on training exercises. Today, I'll show you how to use hyperspectral data in combination with several algorithms to create a tree species map using a supervised classification in the EnMAP-Box. In this tutorial, we make use of an airborne hyperspectral image that was collected with the HyMap sensor. The image shows a forested area to the north of the city Karlsruhe in the southwest of Germany. Very generally, the area covered by the image consists of coniferous and broad-leaved forest stands. Ideal for training the algorithms, many of the stands are rather homogenous, containing mostly a single tree species. An exception is beech, Fagus sylvatica, that does not occur in pure stands. Today, we will conduct a supervised support vector machine (SVM) classification using the original HyMap bands. Then, we will apply a PCA transformation to the HyMap image to reduce dimensionality by feature extraction. Subsequently, we'll conduct a supervised SVM classification again, this time using the PCA components as input. And finally, we are going to apply another popular algorithm, namely random forest, for a supervised classification using the original HyMap bands once more. Let's start by opening QGIS Desktop. Please ensure you are running a current version. In addition, make sure you have an up-to-date EnMAP-Box plugin installed. Instructions on how to install the EnMAP-Box can be found in the info box below. Now, launch the EnMAP-Box by clicking on the EnMAP-Box icon. Let's take a look at the data that we provided for download. In the Data folder, you will find a raster image in TIFF format. As the name suggests, this is not satellite but airborne data acquired by the HyMap instruments over the Karlsruhe area in Germany. Simply drag and drop the TIFF file into the EnMAP-Box. Then we can display the data by right-clicking on the HyMap raster and selecting Open Image in New Map. The EnMAP-Box offers quite a range of pre-configured visualizations. I chose the True Color option, meaning the image appears in a composition similar to what we would observe with our eyes from an airplane. And here it is, our beautiful test site near Karlsruhe. As you can see, there is lots of forest and a few built-up areas. In addition, I want to visualize the same image in another combination of bands. This time, I right-click the image again, click Open in New Map, and select CIR for color infrared. Wow, that is different! In contrast to the true color visualization, I have now included a near-infrared band, among other changes. By grabbing and shifting the purple bar with the map number, you can actually shuffle the displays around. By clicking on the yellow icon in the main menu above, you can link the displays to make the two visualizations even more comparable. Perfect! I think especially in the color infrared visualization on the right, you can determine the different forest stands. Some appear quite homogeneous, while others seem rather mixed. Okay. In addition to the imagery, we also provided a vector file with tree species information for download. We can add it to the EnMAP-Box by dragging and dropping, or, as I do now, by clicking on the Add Data icon in the main menu. Select the DBF file. Here we go. I right-click on the vector file in the Data Sources window and select Open in Existing Map. This time, to add the points to my color infrared display of the image. There are 250 reference points, 50 for each tree species. Now, To visualize how the reference species are actually distributed, I want to adapt the style of the point data. Therefore, I right-click on the tree species file in the Data Views window below the Data Sources window and select Layer Properties. In the pop-up window, I navigate to the Symbology tab. Here, I select the option Categorized and the value Tree Spec for tree species. Once I click the Classify button, I can see a list of tree species that were mapped. By clicking on the entries above, I can choose a more intuitive color for the display of each species. I choose a bluish tone for the 2 oak species, a greenish tone for the conifers, and yellow for the beech. At the bottom of the pop-up window, I make use of the Save Style option to reuse my assignment of the colors later. I click OK, and well, that makes a difference. I can clearly see that the reference points depicted in different colors now are mostly crowded in individual forest stands. These stands contain mostly single species. Hence, they can serve as reliable reference areas to train the algorithm later on. Do you realize that coniferous stands appear in a darker red than broadleaf stands? Stands with beech reference points, the yellowish dots, appear more heterogeneous. Okay, let's look at the spectra in a bit more detail. I close the True Color map to focus on the color infrared image with the reference points. Then, I click on the cursor location icon, as well as on the Spectral Library icon in the main menu above. When I click in the image now, a Spectral Library window opens. It shows the spectrum of the pixel that I just clicked. By clicking on the green plus icon, I can add profiles. While I first clicked near a Quercus rubra, red oak, pixel, I now clicked a Pinus sylvestris, Scots pine, pixel. Do you see the difference in the reflectance of a broad-leaved and a coniferous species? The conifers reflect less in the near-infrared. That's why they appear darker in the image in the selected band combination. I open the attribute table and make use of a cool feature of the EnMAP-Box. I can actually extract spectral profiles from the vector data file. To do so, I click on the little database icon in the Spectral Library menu. In the window that pops up, I ensure that the correct raster and vector files are selected. Then, I need to add some information by clicking the Copy Missing Source Fields icon and select Tree Spec. And here are the spectra of all reference point pixels. Well, all in purple. I quickly delete the manually collected spectra as we don't need them. Now, remember how to adapt the color of your samples? Right-click on the Spectral Library file in the Data Views window and select Layer Properties. In the pop-up window Symbology tab, I go straight to the Style button at the bottom and load the style that I saved previously. Now, the spectra in the plot are color-coded by species. As you can see, this graph is quite chaotic, and it is hard to see where the spectra of one species end and the spectra of another species start. Overall, there seems to be quite an overlap between the spectral signatures of the 5 species. Let's try to make this plot a bit clearer by plotting the mean spectral signature of each species. To do so, I click the blue Processing wheel in the main menu to get to the Processing toolbox. Here, I search for the Aggregate Spectral Profiles tool. In the pop-up window that opens, I select my spectral library and select Tree Spec to Group by Expression. We don't need the name, so I delete it. Select Mean as Aggregate Function for the profiles and Text as Type. For my tree spec, I need to select First Value as Aggregate Function. And of course, I need to save my file. Ready? Click Run. By the way, as with most EnMAP-Box tools, there is a little help menu to the right of the pop-up window. Now, my new, aggregated, spectral library appears in the Data Sources window. I right-click the file and select Open Spectral Library Viewer. A new spectral library with only 5 mean spectra opens. As before, I can assign the species colors that I chose. This plot is a lot clearer. We can see the mean spectral signatures of all broadleaf tree species have a higher reflectance amplitude than the 2 coniferous species. However, bearing in mind the considerable overlap in the upper spectral profile plot suggests that the classification might not be that easy. Join me in our next video to explore what can be achieved.